Okay, so let's talk about that assignment from yesterday, because this is like the last kind of culminating idea on acid bases. So if you look like, say for example, in number 21, okay? So if you look on number 21, there's a couple of things that are vital that you understand, okay? So on 21, you've got calculate the pH of a buffered solution. Now, again, what are the two criteria that you have to have a buffered solution?
Weak acid.
Weak acid and
Salt with a matching anion.
And the anion off of that weak acid, okay? So if you look on number 21, you're told you've got 0.12 molar lactic acid and 0.11 molar sodium lactate. So right away, here's what's happening. Notice on this one, at the beginning, you just want to say, hey, calculate the pH, okay? We haven't added any hydroxide, nothing is happening, okay? Literally, all we have are these two solutions. So, again, I cannot emphasize this enough. If you do not understand what's going on in the reaction, you are randomly writing down numbers and hoping that the chemistry gods smile on you and the oracle randomly gives you the correct answer out of your calculator, okay? That's a bad way to do science. So, here's the whole point. This reaction, because there's no hydroxide, the only thing you have going on is this. You have an acid trying to ionize into anions. That's it, okay? There's no hydroxide. This is not a titration experiment, okay? All this is lactic acid is trying to find its own way in the world. It's trying to reach its own equilibrium. So here's what's going to be different. This is going to start off at 0.12 molar. Now, if it was a non-buffered solution, which it isn't, but if it was a non-buffered solution, what would those two values, the hydronium ion and the anion, what would those start off as? Zeros, okay? Because nothing is ionized. That's if it was a non-buffered solution. But because it is a buffered solution, you're told that, what's that, 0.11. So this is 0.11 molar. Here's your rice chart, boom, minus x, that's 0, x, x, you assume that nothing really changes, that's still 0.11, and that becomes x. Now, at this point, you have two choices to make, depending upon how much of an algebra nerd you are. One option is that you go, oh, Ka, and you can look up that value, is the hydronium ion concentration times 0.11, which is your anion concentration, divided by 0.12, okay? And you solve for that hydronium ion concentration, and you take the negative log of that, okay? So if you're a hardcore, Ms. Burkamp, I love a good algebra problem, and who doesn't, okay? I'll give you that. But this isn't the time nor place necessarily for that, mainly because of the fact that it's actually much faster if you just go, oh, pH equals your pKa plus the log of your anion concentration divided by the concentration of your acid, okay? This is just simple, okay? You don't have to do the algebra. You can just do it in one step, all right? You're going to get the same answer either way. It's just how complicated you want to make it. Now, when you get to B, calculate the pH of the buffered solution by mixing 85 milliliters with 95 milliliters of sodium acetate. Now, here's where this gets a little bit more dodgy, okay, in terms of how this is going to play out. So what makes B a little bit more complicated, otherwise known as more like Kevin likes it, says you've got a buffered solution by mixing 85 milliliters of a 0.13 molar lactic acid with 95 milliliters of a 0.15 molar sodium acetate. So on this one, you got to kind of do two steps. It's still the same reaction, turning into hydronium ions and anions on your rice chart. Now, and this is going to play out on Monday, when we start KSP, which will probably be like Wednesday. The concentrations that you put in there have to be after these two have been mixed together, okay? You have to have the molarity after they have been mixed. So if you look, you've got, 25 milliliters of, what is it? I don't even know. Yeah, 85. 85 milliliters of 0.13 molar lactic acid, and then you've got 95 milliliters of 0.15 molar sodium acetate. So here's what you got. This is what I would do, okay, because I hate decimal places. I take 85 times 0.13, okay, and I would figure out how many millimoles I have of this to start with. And then I take 95 times 0.15 and figure out how many millimoles of that I have. But you have to have the concentration after they are mixed together. So when you take the 85 times the 0.13, when you get that number, then you have to divide it by the total volume of 180 milliliters, because it has to be the concentration after these two solutions have been mixed together, okay? So that's the only thing that makes that just a little bit more glitchy, okay? That's the only thing. So, but there's that. Now, let's talk about number 27, all right? So if you look on number 27, so I can actually see this. So you've got a buffer solution, acetic acid, and sodium acetate. What's the pH of this buffer? What's the pH after you add potassium hydroxide and the nitric acid? So again, on number 27, I beg of you, understand what is happening inside that beaker to begin with, okay? So inside this beaker, since it's a buffered solution, you have both forms and a lot of them. You have a lot of the molecular form of the acid, and you have a bunch of anions, okay? If it was just straight weak acid, you'd only have the molecular form of the acid. If it was a straight strong acid, like hydrochloric acid or nitric acid, you just have the anions there, okay? And the hydronium ions. But because this is the whole point of a buffered solution, is that it's a weak acid and the anion that goes with it, okay? So you have both of those present. So if you look on this, initially on 27A, again, do not put hydroxides, do not put hydronium ion. You haven't added anything to it. This is just a straight ionization. HA turning into hydronium ions and anions. That's it, okay? That's it. That's it. Nothing else. That's it. There's no hydroxides, there's nothing, there's no acid, there's just this. So on this one, you're told that you have a 0.1 molar, 0.13 in 1 liter. Now, conveniently, because it's in a 1 liter solution, and you know the number of moles, it's pretty easy to get the molarity. Why? It's just 1 liter, okay? Now, if it was 2 liters, hey, you'd have to divide by 2 liters. Or if it was 500 milliliters, you'd have to divide by 0.5. They were nice and said, hey, let's take pity on their soul. Let's just make it in 1 liter, okay? On the assignment I'm going to give you, I don't take pity on your soul. Like on that one, I'm going to give you a different volume, but you still have to have the molarity. So here's what you've got. On this one, you've got, what is it? That's 0.10 molar solution.
Be available by connecting TV to the network.
What?
Channel 20, channel number.
He just-
Volume up, down.
He just dictates and it happens on the.
Go, click, explain to you.
So I never remember if it's a touch screen or.
I appreciate how you still try.
Try twice.
So annoying.
Okay, you can start.
Hey, I'm
Okay.
We're not big Celtics, but.
Anyway, so this is 0.10, this is 0.13. I just slam it into the Henderson-Hasselbeck equation. pH equals your pKa plus the log if your anions over your acid. Okay? Slam it in, boom, turn it, burn, there you go. Now, when you talk about 27B, listen to me, what's going to happen on 27B. So on 27B, I'm going to add 0.02 moles of potassium hydroxide. Are you going to care about the potassium?
No.
No, care less. Potassium is just going to be there. It's just going to, all it's doing is bonding to the hydroxide. The potassium is not part of the story. But here's what you have to visualize. When you add that hydroxide into this solution that has a lot of acid and a lot of the anions, which one is it going to react with? Graham? The answer is not C.
Wait, what was the question?
Maybe it is C.
Oh, it's gonna react? Are you asking what the?
Yeah, what's the hydroxide going to react with? The acid or the anion?
The acid,
Why?
because the anion is negatively charged and it wants an H from the acid.
Beautiful answer. Okay? So, and again, you have to start with this reaction. So, what's going to happen is that's going to react with your hydroxide. Now, out of that reaction, what are you going to get? Water and the anion. Okay? Now, here's the story. You could, on this one, because it's molarity, because it's like a titration, you can work in moles, you can work in millimoles. What you cannot work in is molarity. Now, conveniently, this is already in moles. I would just leave it in moles, okay? You can go through and divide by the total volume and get milliliters. No, just leave it in moles. It's a gift from the chemistry gods. Accept it, okay? So, you've got 0.1 moles of this. This is not molarity. These are moles. The hydroxide is going to be 0.02. Your anion is 0.13. And those are all moles, okay? So, what's going to run out first?
Hydroxide.
Yeah, you're going to go minus 0.02, minus 0.02, plus 0.02. So that's going to be 0.15, that's going to be 0, that's going to be 0.08. Now, here's the bigger idea. You look at pH equaling pKa plus the log of your anion concentration over the concentration of your acid. Before you do any calculations at all, is your pH going to be bigger or smaller than your pKa?
Bigger.
Bigger. Why?
Adding hydroxide.
Because your anion concentration is bigger than your acid concentration. You're going to be taking the log of a number bigger than 1. Your pH is going to be bigger than your pKa. Got that idea? Cool. Okay? Now, when you get to C, on C you've got, hey, what's the pH after the addition of 0.02 moles of nitric acid? Now, I'm going to add, in this case, nitric acid. Is nitric acid a strong acid? Absolutely. Okay? Are you going to worry about the nitrate? No, why not? Why isn't that nitrate going to react with anything? It's the conjugate base off of a, so it could give no cares whatsoever about reacting with the water. Because nitrate can sit there and be a snob and go, I got you. I don't need anything. I'm happy. Nitrate one's minus. Water, you got nothing that I need. Okay? Cool. Nothing's going to happen with nitrate. Don't even worry about it. Do not even write it down. Do not let it even be a thought. It's not there. It's not important. However, what about the hydronium ions?
Very important,
Es muy importante. Why?
because they're gonna bond with the anion.
Yes. So the anions are like sailors on leave. Okay? They see these hydronium ions and go, yo, let's hook up. Okay? It's a poor analogy, but it works. Okay? If you ever hung around with Navy guys, you'll know exactly what I'm talking about. So, I'm just telling you.
Yeah, we're not
Okay? So, what's the net ionic equation?
We're going to the Navy, boys.
No, just you.
I'd like to commit.
The hydronium ion is going to react with what?
The anion.
With the anion. And you're going to make what?
Or go to.
You're going to make more acid. So again, I emphasize this. If you do not know what the reaction is, you don't know where to put the numbers. Okay? So, all of your answers on 27 should be in the high 4s to just above 5. Okay? Now, let's talk about 31, which I'm sure Kevin made horribly complicated.
Okay, I'm not gonna be close to whatever answer you put
Okay.
in there. I'm just saying that now.
So, here's the
Not
story.
really close.
You want to prepare a pH of, this is what you're going to do in the lab on Monday, by the way.
Not what he wants.
You're going to prepare a pH of 3.50 buffer, and you have the following 0.1 molar solutions available. Okay, first off, are all of those listed going to be weak acids?
No.
No. Yes.
I mean, some of them are salts.
Okay? But here's the point, right? They're all going to react somehow, and none of them are strong, the conjugate bases off of strong acids, right? So, here's the story. So if you look at these possible combinations, this is what you don't want to make this complicated. So, if you look at the Henderson-Hasselbeck equation, of pH equaling your pKa plus the log of your anion, y'all know the drill from there. What do you want to pick? Do you want to pick one that has a pKa close to 3.5 or one that's far away?
Close.
You want to pick the one that's closest. So all you have to do is go through and take the negative log of those acids. Pick the one that's closest to 3.5. That's all you have to do. Okay? That's it. Do not make that complicated. Did you make it complicated?
Extremely.
What did you do?
I found the actual volumes, but I used acetic acid because I knew 4.74 is the pKa of acetic acid. But I found the actual volumes you needed of them both. You need
It's a problem with being too smart.
No,
Damn it, Kevin. The work is. I checked my work.
literally. Look up the Ka of the acids, take the negative log of them, pick the one that's closest to
3.5.
That's all you have to do. Okay, any other questions on that assignment? Going once. Twice?
Can we get a rundown of the general area of our answers?
For which one?
Any of them, all of them.
15 are in the 4s. 17A is in the 4s. 17B is a really small number.
So to make find the H plus concentration, and then it's just, yeah, that's it. Is that what you're wanting us to explain on 31?
Yeah, I'll take the lost point.
When do you know
I'll take the
you're
lost
supposed to
point on
say
31.
Versus moles or millimoles?
Kevin.
Okay,
I was
if
confused
it's
on that.
any kind of titration where something is gonna get used up, like you're adding on this one,
Ignore.
your hydronium is gonna react, so that's gonna reaction is gonna go until one of these gets used up. So the only time you just work on straight polarity is if it's just like a situation like this, where it's just trying to self-ionize.
Okay,
And
so-
there's nothing added to it. So if
it's just
you
like
add
water.
anything to it,
Yes, okay, that makes sense, cool.
okay,
Good stuff.
does that make sense?
Yes.
Okay.
I did one question.
Did your cousin notice SARS and like out too?
Oh.
Like some PTSD.
I took one look at one of the university,
It's so bad. That's all I do. It is genuinely
Yes,
all I do.
bro.
I can't stop.
or you know, there's gonna be that
It's, I'm so sorry.
She got it in my head.
No, it's been a problem for like this long. Like, Grace is so tired of me.
The entire day, the only thing that's been in my head is,
Wait, is band
"If
doing
I
What that
Like, it's been in my brain constantly. It's just that one thing.
I don't understand how
Right.
the conferences
One
to go every
or
single
two
day and
buckets.
still
One
have
was
no
a
clue about
cubic,
what's going on.
One was like a quadratic.
Goodness.
They cross
So
and
they
make
walk with
two
me like,
separate
what's the day for
sections.
today?
With
Like, it's not class, so it's from school.
Oh, okay, yeah.
area
It's not, it's
between
on
two graphs. You have to, like,
Instagram, we've been talking about it since
Maybe
November.
people
It shocked
don't
me.
do
But
it.
because
It's
the
no
top
why.
function
Next
changes.
week, even when I'm being
Oh.
still
That's
gonna
right.
forget every morning.
I would.
Yeah, yeah. Just
Does anybody want
You
to
do
record
what?
yourselves
Wait,
from
wait,
these
wait.
announcements and come back?
like fully correct.
It's really, it's not that.
Sometimes I just laugh, I'm like, yes, I know exactly
Why
what.
not?
You know how, right, you do.
I'll put a video of you standing there saying in the office.
No.
I know.
I'll literally
I know
stay
I
on
probably
your
should
house.
just
Okay.
So I'm gonna be for 5 hours.
So let's say I gave you this question, okay?
I didn't realize
So
that.
you have a pH versus volume curve. You have two lines. You have like the pencil line, and then you have the blue line. One of those is for the titration of 0.1 molar hydrochloric acid, and the other one is the titration curve for the 0.1 molar acetic acid.
B is for blue.
Which one is which?
Wow, yeah.
B is blue.
That's actually B is blue.
B is for blue.
Why?
Because
it has a
There's two reasons you should know.
Higher pH.
well, there's gonna be less hydroniums in the weak acid because it's not gonna dissociate fully and it's at the same
Okay.
polarity.
So right away, because they're both 0.1 molar solutions, right? So understand that there's like an inverse relationship between pH and the number of hydronium ions. As the number of hydronium ions increases, what happens to the pH?
Goes down.
It goes down because you're taking the negative log of a concentration. So that's the dichotomy. So you're inverse. Lower the pH, the higher the concentration. So if this was 0.1 molar hydrochloric acid, and I asked you to find the theoretical pH, what's the only thing you would have to do?
Negative log.
Of what?
0.1.
Negative log of 0.1, because that's the full ionization of the hydrochloric acid. Okay? That, by definition, is what happens. Oh, if this is 0.1, my hydronium ion concentration is going to be 0.1. Boom, there you go. Now, on your acetic acid, is that going to fully ionize?
No.
No, because by definition, that's what makes it a weak acid. So right away, that even though it's the same concentration of 0.1, your acetic acid is going to start with a higher pH because of the fact that it has a fewer number of hydronium ions floating around. Okay? Got that? So you can look at the beginnings. How could you look at the midpoint of that, where you reach the end point of the titration, the equivalence point, and figure out which one is the weak acid and which one is the strong acid?
The weak acid's gonna have an equivalence point above 7.
Oh, why?
It's gonna have an equivalent point at 7.
Why? It's a beautiful answer. Why?
Because when the HCl, it fully dissociates, when it's at equivalence, it's equal, but the weak acid's not. I really just remember it from the lab.
Oh,
Like,
because
I
the
could be confused.
Yeah,
The strong
the
acid's
magic
gonna all
thing
become
happens.
salt and water, so it'll just be water, which is 7, and then the weak acid's gonna have that weird like secondary reaction stuff messing up and doing the bases.
Yeah, that
Base
magic
lines will be
stuff.
higher than
Okay,
that.
let's articulate this a little bit more.
That
That leaves the hydroxide, not the bases, but you know what I mean.
Let's use.
Just say the
let's
magic
use-
though, and
Let's
move
use
on.
chemical, let's use our chemistry words.
No, it
No.
does the thingy,
Cohen?
it makes the thingy.
It does the thing, and magic happens, and then it's above 7.
Okay, let's,
The oracle tells me the answer.
let's use our chemistry voice. Okay,
Chemistry voice.
right?
I love my work.
I think you want to take my
Shut up.
So,
Shut it. Shut it. Stop.
if hydrochloric acid reacts with sodium hydroxide, what do you get?
Water and
Salt, water.
salt.
Salt water.
Yeah.
True?
Delicious.
Now,
Lucky Charms. You said delicious.
you have sodium ions
Delicious.
floating around and you have chloride ions floating around. This is important. Are either one of these going to react with the water to alter the number of hydronium ions or the number of hydroxide ions?
No, they're cool.
No, the sodium could care less. It's lost 1 electron, it has its 11 protons, it's stable as all get out. Chlorine could care less, it has its 1 extra valence electron, it's the conjugate base off of a strong acid. Both of these are snobs going, hey, water, you're cool, we're cool, let's just call the whole thing off, okay? There will be no frolicking or interaction between that cation and that anion.
What?
They are in the solution, okay? The sodium ion and chloride ion is in the solution, but it doesn't do anything to alter the pH. Because remember, to alter the pH, you need to do one of two things. You either need to change the number of hydronium ions, or you need to change the number of hydroxide ions. If it is a strong acid, strong base titration, nothing happens. Okay, they're there. I'm not saying they're not there, but they're just like, whatever, I'm cool. Go away. Okay? However, what would the net ionic equation look like for that? Owen?
Whole wheat pita chips.
H plus OH minus turns into H2O.
Boom.
Watch out.
There's your net ionic, okay? Care less about the sodium, care less about the chlorine. Basically, you're going to take a proton, hook it up with a hydroxide, and you're going to make water. That's your net ionic, okay? Nothing else matters, because everything else is just going to watch the solution, watch the reaction take place. However, if I titrate acetic acid, HC2H3O2, and sodium hydroxide, what are you going to get out of that?
Water.
Water, and technically you're going to get
Sodium acetate.
sodium acetate. Okay? Technically there's like the Chem 1 version of the reaction. It's not what I want. I want the net ionic because it shows you what is really happening in the reaction. So on the net ionic, you have to get this right on this net ionic.
Keep it clumpy.
Are you going to separate that? Or in the words of Kevin, are you going to keep it clumpy? We're going to keep it clumpy. Why? It's a weak acid. It doesn't ionize. It's staying there as the molecular form. So this is just when you start to do that net ionic. If it is a weak acid, keep it clumpy. Okay? Keep it clumpy. Maybe that could be the AP chemistry teacher. We keep it clumpy
That's
in the hood.
that's it.
Okay.
What?
Just an
Keep
idea.
it clumpy. But
Now, what about the sodium? Are you going to care about the sodium? No, don't care. Are you care about the hydroxide?
Very much so.
Very much so. Okay, very much so.
I mean, yes, but
Water? Do I care about the sodium over here?
no.
Do I care about the anion?
Yes.
Yes. Yes. Yes. So there's your net ion. See the difference between the two?
Yes.
Non-clumpy, clumpy. Okay?
On the top
What
one.
is happening?
What happened from yesterday, Charles? You
Because
said
no, I
something
like,
yesterday.
I understand it, but
The
I don't
anion's
know
still negative when it
why
has
we're
sodium
doing
attached to
it.
it.
Because weak acids.
We don't know why weak acids.
Weak acids
Oh,
will
that's-
exist in the
That's-
solution
yeah.
as
That's-
I was-
form.
No, no,
I was
no,
like, it's
no,
bonded.
no,
And we don't
that's
know
valid.
why
That's-
weak acids just be saying something.
Okay.
But like,
Now-
we do,
But
but
what
I'm
are
not
we
gonna
doing
bore
with
you
this?
with that one.
Your net ionic equation should balance on two things. What are the two things it should balance on? Charge and number of particles.
Yeah.
Okay?
That's
You
both
have
ways.
to put the charges on the net ionic. Is there a charge on the molecular form of the acetic acid?
No.
No, because it's neutral. Okay, it's clumpy. All right. Now, if you have 10 millimoles of this and 5 millimoles of this, right away, what's your pH going to equal?
PKA.
pKa. Ooh. Why?
I didn't say that. I said PKA.
It's half neutralized, right? You go minus
I
5,
understand, but I don't know what's happening.
plus 5, plus 5. Your anion concentration equals the concentration of your acid. You're taking the log of,
One,
which is,
zero.
so the pH equals your
pKa.
pKa.
Which is 4.74.
No, I shouldn't. For any number of reasons, I should. For any number of reasons, I should not.
Why'd
do
we
that.
add hydro?
That's what I'm saying. I was literally about, I was
That would be so bad.
Hey, I can't be around pom-poms anymore.
Get the crop top on.
I've never.
Hey, yo.
I dislocated my
Although two of
knee.
my sisters.
That's the AP Chem.
Last time I helped.
Now, what if this happened?
Oh no. Oh, we're good. Okay.
Me and you were thinking the same thing.
Now what's gonna happen?
Then the second reaction will kick in.
Ooh, now I'm gonna go minus 10, minus 10, plus 10. So is anything of this left in the solution?
Not.
It's completely neutralized, gone.
Which means we have to do that second.
Oh, now you gotta do the second thing, right?
I'm understanding.
Are you getting it? Are you getting it,
I
Chuck?
mean, yeah, kind of. I know what to do next.
He
I
knows
know
what
why.
he knows the math. He does not know why.
That's it for birthday.
The
The
math is
concepts
what
are
it is.
still not grasping my brain.
Okay,
Brain's supposed to grasp the concepts,
Yeah.
the concepts.
why does this start?
Why?
Why does this start a secondary reaction?
Mutual relationship.
Because the anion is the conjugate base off of a, so it wants to reform and get
Clumpy.
puppy. Okay, let's get puppy. Okay, so
Wait, let's get clumpy. It's kind of making sense now.
I just had to put it in a
Why
rap
are you
form.
surprised?
Is that it?
You should make all your lectures rap. Yeah, the weak acid, it likes to reform
No,
the
no,
weak acid,
stop.
yeah.
I need you to yell at mid-test.
I've
Charles.
had a career in music.
And by the way, on the test, if you invoke the clumpy clause, I'm good with that.
Would I get extra credit if I put?
No. So, here's what's gonna happen. What are you going to get out of this reaction?
Acid and
You're
OH.
gonna reform the acid and
A hydroxide.
Hydroxide.
hydroxide. What does the hydroxide do?
Turn it basic.
Because you're generating hydroxide, so the pH should be above
7.
Yes.
Plumply.
Ah, things are clicking.
Now,
I
Staying on
my
business,
adverb
Chuck.
nickname.
when you do this, when you're doing this secondary reaction, you have to do two calculations. Does this, on your C2H3O2, is that going to be millimoles, moles, or molarity?
Molarity.
That is only molarity. It is not millimoles, it is not moles. So what you have to do here is take the number of millimoles and divide it by the sum total of the volume in milliliters. What are you going to start these off as? Zeros. Minus x, plus x, plus x. So this is going to be the number of millimoles divided by the sum total of the number of milliliters, x. Because it's acting as a base, what do you have to find?
KB.
KB value. And that's easy to do because your Ka times your Kb equals 1 times 10 to the negative 14th, which is not water. Okay? Cool with that?
Yep. Sure. We're locked.
Okay. Promise you, there's one more quiz over acid bases. And there's gonna be one big honking test. I promise you on both of those, if you have not done these steps, you have done something horribly wrong.
Is this gonna be one of those tests, like you drop it and the one half of the table lifts up from how heavy it is?
Like Chase physics.
What do you
Okay,
mean maybe? What do you mean, that's not the response? It's like, no.
That's a yes or no.
How many pages
I
is
can
that?
lie to you.
It's a yes or no.
I like that. Can you lie to me?
No, I want
Okay.
them to prepare with have some impending dread.
Look, I don't wanna have the fear. I only wanna have the
Today,
fear for the
after
90 minutes that I'm thinking.
Okay,
Oh, watch
so
this.
Kevin,
Yeah,
stop
yeah.
the other camera, bring that, we're gonna go to the back.